All right, good afternoon, ladies and gentlemen. My name is Aditya Mathur, and I'll be presenting this technology called SafeCrit. And essentially, I'll be focusing on a, a strategy that we have been using, which is to fuse AI and design to protect critical infrastructure. The other three authors that you see here, Gautam is one of the guys who, he's an AI expert, so some of the work that I'm describing is from Gautam. Siddhant is another expert who has been looking at our technology for plant protection. And Tiger and Siddhant both have been working on plant protection. So let's go here. Now, critical infrastructure, I think, as you all know, I won't go read this thing. The US Patriot Act of 2001 actually defined what critical infrastructure is. Water, power, maritime, all these systems are in the area of critical infrastructure. In iTrust, we focus on water systems, treatment systems, distribution systems, and electric power systems, in addition to IoT devices. Just a brief on on iTrust. So iTrust was launched in 2012 by the Ministry of Defense in Singapore, and we had funding from Ministry of Defense. 2013 to 2018, iTrust grew quite a lot. We had significant funding from National Research Foundation and PUB. Then 2019-20 also saw expansion. We had a tech transfer. We have transferred some of or licensed some of our technology to a startup in Atlanta, United States. And then in 2021, MINDEF is back in a big way with iTrust. So now iTrust works very closely with MINDEF to conduct exercises and develop technologies. iTrust has focused right from day one, 2012 we started. Our focus was exclusively on the defense of critical infrastructure. And we looked at, as I said, water treatment, water distribution, and electric power. Now, we have 19 faculty members overall, which includes faculty from all the 4 universities of higher education in Singapore, about 13 research fellows, 12 research assistants, and 9 staff members. Our focus, as I said, is design, develop, and deploy technologies to protect industrial control systems against extreme attacks. So as most of you probably know, an industrial control system consists of SCADA systems, engineering workstations, HMIs that are controlling a plant, generators, valves, pumps, etc., etc. Now, one of the, I would say, a unique feature of iTrust is our test beds. So right from the beginning, when we started the center, we asked ourselves that we are going to develop technologies, but how are we going to test these technologies? Of course, it is very difficult, almost impossible, to test a defense technology for critical infrastructure in a real plant. For example, I cannot go to a real water treatment plant and say, hey, I would like to attack your system and test my technology. Obviously, no. So what we decided was we'll build test beds that are sort of scaled-down versions of actual systems, and then we will allow our students, researchers, and our collaborators internationally to actually launch attacks on these systems. We'll also allow our researchers to integrate their technologies into these systems so that the entire cyber exercise of red teams and blue teams can be conducted on these systems. So this was, I think, a very good decision that we made in 2012, and then since then, starting from 2015, to about 2018, we have a collection of test beds that were created. And as you can see here on the top left, we have a water treatment plant, which is called SWAT. And then on the top right, we have a water distribution system. These two are connected. So the water that is treated in SWAT goes into the water distribution system. And on the bottom left, we have a shielded room, which is an IoT room, where we can actually conduct complex attacks, such as GPS spoofing on various devices. On the bottom right, we have the electrical power grid that is connected to the water treatment plant and the water distribution plant. So we can actually launch attacks on one system and look at its impact, cascading impact on other systems. And we have done research, published papers on something like this. The problem that we are really interested, have been right from the beginning in solving, is the following. So first of all, we define something called an extreme cyber attack. So an extreme cyber attack is one where the attacker has access to plant controls. Now, how this access has been achieved is another matter. It could be through the network, or the guy is sitting right in front of the computer, or the guy is in another country, but he has the access credentials, and so it doesn't matter. But the access has been achieved, and therefore this guy has the ability to turn on, turn off devices like pumps, generators, etc., and also to manipulate the data that is moving on the plant network to deceive the controllers and so on. So that's an extreme attack. Okay, that's the extreme attack. Now, the problem, therefore, is how to effectively protect a water treatment plant against an extreme cyber attack. By the way, I'm focusing on a water treatment plant here simply because some of the data that I'll be presenting is from our water treatment plant and also from another public water treatment plant in Singapore. But the technology in general that we have developed, especially the design-based technology, is applicable to any physical system. And we have tried it on both water treatment, water distribution, and electric power plant. So the existing solutions, if you see, are you have an asset, okay, which could be a plant, for example, and you create boundaries around those assets. Okay? So there's a physical perimeter. For example, if you go to a water treatment plant, there'll be a physical perimeter. In some cases, that's not possible. Like in Colonial Pipeline, the pipes are going thousands of miles, and also in water distribution systems, you may not be able to put a physical perimeter. But in many cases, you are able to put a physical perimeter. The other is cyber perimeter. So you put firewalls, network intrusion detection systems, etc. And then you have management policies. For example, there will always be maintenance guys coming. You have contractors who are coming and going, and you'll have policies, don't allow them to use their laptop for this or that, and so on. So these are the protection mechanisms that already exist in almost all the modern critical infrastructure. What we do on top of this, we add something called anomaly detectors. I think most of you are familiar with anomaly detectors, and plant protectors. So anomaly detector is a technology which is now quite advanced, and I would like to say that we are some of the first ones who created anomaly detectors for critical infrastructure using design technology. And plant protectors, I've not seen anywhere else other than in iTrust. And together, these two technologies we named them as SafeCrit. This technology has been licensed to a company in Atlanta. So let us look at the access routes that an attacker can use to launch attack on a critical infrastructure. Now, in this diagram, of course, I have simplified a critical infrastructure. It'll have controllers, it'll have a plant network, it'll have business logic, and of course, the plant. Business logic may or may not be connected to the plant network in any way. Okay? I'm not saying in this diagram it shows that it is connected, but it may or may not be connected. Also, some people say that, well, business logic should never be connected. Some people say, hey, sometimes it is necessary. We need business logic to be connected to the plant. So I'm not claiming or saying that it should or should not be connected, but both possibilities exist. Now, through the network, of course, people can come in and they can access the plant network via the controllers. That is one possible route. They can also come directly via the plant network. They could also come via business logic network, and probably that's what happened in Colonial Pipeline. And in the worst possible case, they can come directly from controller, which is the insider attack. So these are at least 4 potential routes to a system that is to be attacked. And you might think of some other routes also and so on, but at least these are the 4 that I think are pretty much most prevalent routes to the critical infrastructure. Now, as far as the existing solutions are concerned, if you're talking about an attack directly from the controller, which is a SCADA system or an HMI, on the plant, then all you have in many systems are firewalls and network intrusion detection systems, which could be in the plant, between the plant network and business logic, or it could be also outside between the business logic and the internet. However, this protection, firewalls and etc., is not going to help in protecting the plant against this kind of an attack. This is the extreme attack that I'm talking about, where the adversary has gained control over your SCADA system and now has pretty much anything that they can do. This is where we come in a pretty powerful way. So there are 3 strategies that we have been deploying in order to understand and create some of the very powerful technologies. The one technology is based purely on AI. So we have people, as you know, nowadays, all the youngsters who come out of college, they love AI. AI is a big word, and they all want to create technology using AI. So we do have research that actually takes data from a plant, operational plant, and creates models of the plant behavior. And then these models are used to predict the plant behavior, and that's how the anomalies are detected. So that is one of the ways. The other way which we have used is combining AI and design. And by design, I mean the plant design, that how the different components of the plant are connected with each other, which you will see in a typical HMI or SCADA screen. And plant data and plant design are used to decide what models should be created, and then that's how we create the anomaly detector. So the key difference between the first one, AI and AI plus design, is in the second one, the design of the plant is used to identify or to sort of discover what models should be created based on the dependencies of the different components in the plant. The advantage of this approach is, one advantage of this approach is that you create multiple models, not a single model. So in the first case, you might create a single model, and a lot of, I had heard from several professors in universities, oh, give me the data for the plant, I have powerful computers, and I'll create a model and that'll work fine. Actually, it never works fine. It never works fine in a large plant if you create a single model for the plant. So that's, I think most people now realize that. So with the help of design, you create multiple models of the plant, of different portions of the plant, and then use these multiple models to find out whether the plant is operating normally or not. But the key sort of novelty in our strategies is here in design. So right from the beginning, we said, my university, SUTD, is a design university, Singapore University of Technology and Design. So we said, well, okay, AI is a big thing, no doubt, but can we use exclusively design in order to create anomaly detectors? So there was a PhD on this topic, and we found out that if you do that the right way, okay, if you do that the right way, which means you really understand the design well, and you create your what we call as invariants that are essentially rules, and you deploy them correctly, you program them correctly, it is almost impossible for an attacker to launch an attack on the system that will not be detected. So this technology of using purely plant design to generate an anomaly detector has been our gold standard. The issue with this technology has been that if you have a large plant that has thousands of sensors and pumps, et cetera, actually creating these invariants manually is almost impossible. And therefore, what we did was we have created a tool called Aegis, which actually takes the design as input and generates the anomaly detector as its output. And most of the work is done automatically, which actually reduces the chances of error in coding and also reduces the chances of missing certain relationships across plants. Design essentially uses physics and chemistry of the plant, where we cannot go wrong unless we make an error in understanding that physics and chemistry. So the fundamentals of physics and chemistry are used in this third strategies. So these are the three strategies that we have used in the past and evaluated intensively. So what we do is, now the important point here is, I talked about anomaly detection. Now, I think all of you will agree with me that anomaly detection is essential. Detecting cyber attack is an essential component, is a necessary component of any defense mechanism. You must be able to detect. However, anomaly detection is not sufficient. Okay, so my anomaly detector says, this pump should be running, but it's not running. Or this tank is low, and the pump is running. Okay, so what do I do now? And why has this happened? So there is a huge amount of work to be done once an anomaly has been detected. And so anomaly detection is necessary, but not sufficient. So what we do is we created something called active protection, which actually creates a set of tools, anomaly detection and protection. They work together. And therefore, we have the necessary and sufficiency conditions satisfied. It is still not complete because eventually you have to somehow remove the attacker from the system, because you cannot be defending constantly if the attacker is there continuously in the system. So the third part, that is removing the attacker, is something different, which we haven't worked much on that right now. Then the third important thing here is, when there's a ransomware attack, one of the key problems that is faced by the CIOs, CISOs, and the management and the operators is the availability of data. you may lose, chances are you will lose your insight into the plant. So there's a ransomware, sort of a request or not a desire. Give me $5 million and then I'll release your plant to you. Okay? But the guy doesn't have control over the plant. It's not an extreme cyber attack. The guy only has managed to put some sort of a page on your screen, and you are scared now. But you're not getting the data from the plant. And people are asking you what's happening. You said, I don't know what is happening. So what will you do in such a situation? In a critical infrastructure, you shut down your plant. That's what happened in Colonial Pipeline. They shut down the plant. And then you know what was the consequence. So what we have done is, we have created a separate tunnel so that in emergency situations, you can continue to visualize your system data and performance. Of course, you may ask, can this be also attacked? So of course, we try our best to create a completely separate system which is not connected to the internet, et cetera, and hopefully that will not be attacked. So these are the 3 plant defense mechanisms that we have created in iTrust, and we demonstrated on our systems for total plant defense. Okay, so the issues, as I said earlier, we are talking about AI and design. So there are some issues with using pure AI. And one is unwieldy models requiring exceptionally large amounts of data and time to train. So, of course, one can argue we have powerful computers, supercomputers, et cetera, graphics card, and so on. So, yes, that helps, but you still have unwieldy models and large amount of data. Then you have a lot of AI goes into feature selection. So you do feature selection. Okay, this plant has thousands of features. No, this feature is not that important. This feature is not that important. So you do a lot of data analysis to figure out which features are important, which are not important, and you ignore the features that are not important. Now, that is a risky bet because you think those features are not important. Why? Because they don't appear in the data in any significant way. But actually, in a plant, they may be important at certain times, maybe during safety, when safety mechanism comes in and so on. So that is a risky thing that AI guys do. Then it also lacks in localizing anomalies. Where exactly has the anomaly occurred? So the anomaly might have occurred here. The attacker might have attacked a valve somewhere, but the impact is here, and the detector is showing the impact here, but actually the attack was on something else. So this is another issue with pure and AI-based. Then, of course, one of the major problems is false positives. So you keep on tuning your AI system. Keep tuning until your false positive reduces to almost 0. So that's a long process. But then you have tuned and you said, bye-bye, operators, now the the anomaly detectors are under you. Okay, the guy goes away, and your anomaly detector is installed, and then suddenly there's a change in the plant parameter. Boom, anomalies start coming up. So this is another issue and now you will say that, okay, so what do we do with the anomalies? You retrain the system. Again, another major time hogger. And then, of course, that's why I said frequent relearning may be required, and hence redeployment due to change in plant operational mode settings. And finally, the failure to detect situations where there is no anomalous network traffic, but there exists process anomaly. So there are several anomaly detectors that work on network traffic. It is possible to launch attacks on a system where there is no network anomaly, absolutely nothing. Network is fine, but your plant is behaving badly. And so if your anomaly detector is focusing exclusively on network traffic, sorry, it is something which is existing useful technology, but it will not detect many attacks which are really on the plant. So what we have done is we use AI and design. Of course, we have pure design also, but today I'm only talking about AI and design. So the advantage is you get simple models, and the data volume is lower for creating each module. Physics is used to decide which features to be selected, and not data, and exactly identify and report the compromised component under threat. You can do it much better than pure AI. And then the number of false positives is near 0, and you have limited retraining and retuning. Of course, the retraining is still required. We are still having that problem of retraining if you use any form of AI, even if it is with design. So that is an issue. And it is designed to detect, of course, OT anomalies. So far, we have not focused on network anomalies. Right from the beginning, we decided that we'll focus on OT anomalies because there's a huge amount of work already and commercial tools available for detecting network anomalies. Now, the design-based solution, of course, that we have, pure design-based solution, has extremely high accuracy, ultra-low rate of false positives. It has the manual generation, of course, as I said, is impractical, and therefore it needs automation, which we have almost done now. And so our solution sits like this. You have the same diagram that I showed you earlier. And SafeCrit technology, the beauty of SafeCrit technology is that it can sit anywhere you want. So because we have the plant under our control, we make it sit inside controllers on the plant network and inside the plant. In a real plant, legacy plant, the plant management may not allow you to do this for various reasons. And therefore, your SafeCrit technology might only sit near the historian. So it may not be any of these places. It might be outside the plant next to the historian. So that is not the best way, but that is a practical way in legacy plants. But our technology is actually the best possible, I would say, technology for use when you're designing a new plant. When you're designing a new power network or you're designing a new water treatment plant or whatever, this technology should be used right at that time. That's why we started by, earlier when we started, we said it is security by design. And many people talk about security by design, but what does that mean? And this is what our design technology meant, that is you install it at the time you're designing the system, not 20 years, 10 years later. So just to summarize this thing, we do pilots. We do pilots on our test beds. We also do pilots on real plants. So if you see here on the left side, on the leftmost column here, pilot 1 was done in May 2020 using pure AI. We launched 48 attacks. This was on a real plant. I cannot disclose what the plant was, but it was a real plant where the water is actually being consumed by actual users. We launched 48 attacks, and 34 were detected. So the detection rate was 70.83%. Surprisingly, over 8 hours, we ran the attacks system over 8 hours, 4 hours on one day, 4 hours on the other day, in front of plant operators and senior management from the plant. And there were no false alarms. 0 false alarms over 8 hours. This was a big surprise to the plant engineers because they already had installed technology for anomaly detection. That was generating a lot of false alarms. So they were quite surprised. Then we did another pilot, which is actually ongoing right now. So I don't have all the results of that, but I'm only giving you a part of the results. This ongoing pilot is using design and AI technology. Not only AI, design and AI. We launched 34 attacks. And then all 34 were detected. We are still saying 99.9% because one of the attacks took quite some time to detect. And again, 0% false alarms. We also do exercises. So the last column, the rightmost column, is based on the exercise that we did in 2021, which we do annually for the last few years. In this, attacks were launched by people from various parts of the world, from various militaries located in France, Germany, Australia, and so on. And a total of 25 attacks were launched, and 23 were detected. So this was 92% detection rate, and again, no false alarms. And the 2 attacks that were not detected were because the guys were smart. They actually disabled the historian. And our detector was receiving the data from the historian. It stopped receiving the data, so it could not detect the attack. So obviously, that tells us the location of the detectors. Where should they be located? If you locate them in the historian, then you may have a problem. But the attack on the historian was detected because we have a blockchain-based technology that detects attacks on the historian. So the attack on the historian was detected, but not by this detector that I'm talking about. So that was quite beautiful. Essentially, we detected all the attacks. This diagram just gives you an idea of the pilots, how we perform the pilot. So if you see on the leftmost, we get the plant data, and we actually put the data diode so that our technology does not send anything back to the plant. This is how we convince the big plant management that we can do pilots and we will not affect your plant. So if any one of you here from any country wants us to do a pilot on your plant, this is how we will do it. And we are right now in the process of getting some pilots in the United States, some of the water treatment plants there. So the one problem we have is, of course, how do we test all this? And I told you how we test it. So we have this DAD, which is a pure design-based detector. We have AI Kit, which is our AI and design-based detector. And we have the plant protect mechanism. So we put this in the plant. But then when you do something like this on a real plant, whether it is our test bed or a real plant, the time to do the experiment and the number of experiments you can do is limited. You cannot run the plant at a rapid speed. The water treatment plant will run at the speed that it is running. You cannot simply increase suddenly the speed of this or the speed of the valve to close and open and so on. So therefore, what we did was we created something called a digital twin. So for the water treatment plant, we have a digital twin that was also used twice in lock shields. And we use this digital twin to conduct our exercises as well as to evaluate our technology. This has been very useful because we first put our technology into the digital twin. We connect it to the digital twin. It gets the data from the twin rather than from the actual plant. And then you can find out how well your technology is working. And you keep on improving it. Once you think, hey, it's good enough, then you put it in the actual test bed and you test it there. You improve it. And when you are pretty sure that, hey, this technology is robust, powerful, then we go on the pilot in a real plant. So that's the strategy we have been using so far. So, of course, why use the digital twin? Because it enables execution of tasks, among others, that may be too risky to or simply infeasible to perform on a twin plant. And that's what. So I'll just give you a brief on architecture. So SWOT, as I said, this is our SWOT test bed for which we have created the twin, which is used in lock shields. It is a full 6-stage plant. You have raw water input at the left. Then the water goes through chemical dosing, ultrafiltration, dechlorination, reverse osmosis, and backwash. You will find all these processes in a large system, but our plant, of course, is a scaled-down version. Instead of a tank that has 100 million gallons of water, we have only a few gallons of water and so on. This twin that we have is fully virtualized, which means every PLC is in a separate VM. Every RIO is in a separate VM. Every valve is a separate process. Every pump is a separate process, and so on. So when we actually install this twin in lock shields, we actually install it as a distributed system so that the attackers can launch attacks and it becomes more and more challenging for the defenders. And of course, this is actually what happens in a real plant also. Every real plant has an industrial control system that is distributed across the plant through PLCs and so on. We have a SCADA to which you can connect anomaly detectors. So you can actually rent the twin from iTrust, and you can create your own detectors, and you can hook it to the twin, and you can test out your own anomaly detectors or your own technology. Last year we released our twin to our own students, graduate students in SUTD in Singapore, and also to students in Bristol in UK. And I think we have permission to actually use this tool for research and education. So if any one of you is in a university or want to do research and want to use the twin, you're welcome to contact us. All right. This is just a view of our SCADA system for our twin. Surprisingly, if I say that this is the SCADA view of our actual plant, I will not be wrong because they are identical. If you see the two plant as well as the twin on side by side, you cannot figure out which one is which. We have a state visualizer, which actually is a very professional looking system, which can actually show you the actual plots of various plant components in real time. We have an attack desk. This is a beautiful tool that was developed by one of our interns. So you can use the attack desk to design attacks in advance. These are scripts, small scripts in Python. You can save them in a database, and you can, whenever you want, you can launch these attacks on the twin as well as on the real plant. So we use this quite often when we do the demonstration of our technologies. Thank you very much. I'll be happy to take questions. Yes, sir.
Hi there, Scott from UK MOD. I've actually done block shields before and I've seen this in operation. It's very impressive. You talk about building a digital twin like it was quite straightforward, but I suspect
Yes. Okay, so there's a long history, and we have a slide outside which actually shows you the details. But in brief, the idea of digital twin came to my mind in around 2017 because I was teaching a class on cyber physical system security with another professor. And every time I would go to the class and I will just talk about these plants, and the students were not able to actually get their hands on something. And so I started development of the twin in around 2017. Gradually, it was an incremental development process, very agile process. Gradually, it developed to a point where in 2020, I think we showed it to the CCDCOE folks here, and they thought that it was a good thing. Then MINDEF also saw it, and they were pretty happy with it. And then after that, so at that time, we did not have this beautiful HMI that you see. So one of our research assistants built this HMI. And so it has grown gradually over time. If you look at the code, you will say, this guy is terrible. Okay. So the code doesn't look nice to me. I'm a software engineer by training. But now we are redoing the twin so that it looks nice. And we are actually creating something called a twin generator, which will work for water treatment plants. So if you have a plant which is different from the plant that we have, all you will have to do is to create two files. One file will have the components, the list of components, pumps, etc., etc. The other file will have the parameters. So this valve, for example, takes 6 seconds to open and close, and so on. These two files are the only files that you will need, and you feed these to the twin generator, and out comes the generator. Not totally correct, because the controller might be different. So you may have to do some manual work on the control logic, because the same control logic might not work, especially if a plant is different. But most of the twin will be generated automatically. That's what we are doing now, but we have not completed that work. Yeah. Yes, sir.
I realized that you soft-coded seemingly the sensors and the actuators.
Yes.
To your experience, in which industries does this come to a limit? The background of my question, I've seen the equivalent now of the electrical power plant installation, and I've talked to their engineers, and they said for certain purposes, you really have to have physical devices attached. Could you comment on that aspect?
I think that's a very good point. So there are a few challenges that we face when we put these devices and, as you said, soft code them into the twin. One is, if you look at the plots of our data, it looks pretty straight, no noise, which is not the case in real life. So motorized valve in real life will not always close in exactly 6 seconds. Okay? Sometimes there'll be some changes, 7 seconds, and so on. So in the twin, what we have done is we have added a feature to add noise to the data. So to try to make it realistic. I'm not saying it is still totally realistic, but you can control the Gaussian noise and its parameters to make the noise realistic, and then you will see the graph, which is more like a real graph in a plant. So that's one thing we have done. The other challenge we face is in creating faulty components. So right now I'm in the process of creating models, because one of our sponsors, they want us to create fault models in the twin so that we can simulate. So for example, the twin can be run at huge speed. You can run the twin at 1 second speed, or you can run it at 100 times the speed. So when you do that, you can run the twin in 1 day so that it simulates the plant operation over 1 year. Okay? Now, during this 1 year, I can say that, well, this pump may fail. So I can actually create a model for that pump so that it will fail, and that will give you a more realistic view into the system. So we haven't done that, and in our code, we don't yet have the fault models, but that's what we will plan to do. So these are the two main things, I think, which make our twin sort of not as realistic as a real plant, a real pump and valve. Yes. So I thank you for that question. Very nice. Okay, any other questions? Yes, sir.
I add one. Because I talk to industries, I'm working with critical infrastructures that have cyber physical systems which are completely different from water treating plants, railway systems. If one would put it to the test, could you imagine building a model of a train network with the controllers?
Yes, I would say yes. And I would say because a model of a train network was part of my PhD thesis 50 years ago. But that was not a twin, that was a model. And there's a difference between a simulation and a twin. I mean, at one point they can be together, but if simulation is detailed. But the way in which we have built these twins, I have started believing that yes, you can build twins for very complex networks. I would not say that it's an easy thing to do. I think what he was saying was right. It is not an easy thing to do. The first thing that you need before you build a twin is the domain knowledge. You have to be really an expert. I was no expert in water treatment plants, but because we had the test bed, and I was going every night, I would go to the test bed. It was like almost like my second partner, you know. So I would go there and look at how it is functioning, look at how the components are connected, and that is what led us to actually create a twin which is quite close to the real operation. So if you ask me to create a network, a twin for a railway network, I would say yes, but I will have to understand, or whoever does it has to understand. So that domain knowledge is absolutely critical. But the answer to your question is yes, you can create twins for large-scale complex systems, cyber-physical systems, yes. And they would be very helpful for research and education, for training also. All right, thank you very much. Thanks. Oh, Gabor, yes. Sorry.
Sorry, I was just here, and I'm Gabor Vishki, technology researcher at Cooperative Cyber Defense Center of Excellence, and I've been dealing with industrial control systems in the last few years. And I just want to emphasize the role of iTrust, how they help our work in research and exercises, and I would like to say thanks for you to being here, for all the team. I think it's a very nice and flourishing cooperation between the partners like CCDCA and iTrust. So thank you, and I hope that you enjoy to be here.
Thank you very much. Thank you.